Hello, in this video we're going to take a first look at circular motion. There's lots of things that move in circles or very near circles. You've got, a pendulum moves on part of a circle when that's swinging backwards and forwards. You've got a centrifuge, spins things in circles. So does a washing machine. It's much the same sort of thing. Salad spinners, satellites orbit the Earth in things which are very close to being circles. You've got mass spectrometers, you've got fairground rides, things, London Eye, things like that. So there's a lot of things that move in circles. So it's worth taking a closer look at them because then we can become slicker and more efficient in how we analyze them. There's not actually anything new in this compared to the analysis of motion that we've looked at previously. We're going to use exactly the same techniques. We're just looking at the specific case of circular motion just because it comes up so often. So as I say, it's a particular case, but it's nothing special. But first of all, we need to get some terminology down. Let's think about what's actually happening here in circular motion, and then we can see how we're going to go about describing it. So we've got some center of the circle here. I'm just going to draw out a rough circle around this. We've got some object, say it starts here. For some reason, I always think about moving in an anti-clockwise direction. I don't really know why, but it doesn't matter. You can move in either direction. This is at a radius r from the center. It's a constant radius all the way around. It is a circle, unlike what my picture seems to be showing. Right, so how are we going to go about analysing this? You'll see here I've mentioned a couple of things. We've got angular velocity and we've got radians. So up until now, we've just been looking at this linear velocity, so or a speed or something like that. So we could say here this object is moving at this particular point when it's here at this dot. We could say, well, it is moving with some speed v, and say it was moving at a constant speed. So when it gets round here, well, it's still moving at a speed v. And it's doing this all the way round. So you can see the velocity is necessarily changing because the direction is changing, even if it's staying at a constant speed. Now, we will be using that at some point, this v, this speed, but it's not the only way of describing things. So we could say, well, moving between these 2 points here, we've moved through some angle theta. So whereas v is looking at in units, we've got meters per second, say we've got the change in the distance over the change in time. So distance over time there for the speed, which is what we're familiar with. If we were going to go to angular velocity, which is denoted with an omega, sort of slightly more curly w, this is the lowercase Greek letter omega. Well, we could say instead that we're looking, rather than at distance over time, we could be looking at the angle over time. So what angle have we moved through per second? So that's what we can be looking at instead here. Because then if something is moving at a constant speed around the circle, it's moving at a constant angular velocity. It's moving through the same amount of angle every second. So I can put that omega on this arrow here, which is curving around with a circle. So we've got two different ways of describing how quickly something is moving when it's going in a circle here. And we're going to use both of these, the v for the speed and the omega for the angular velocity. Other things that are going to be useful to know are the period. So this is the time to complete one circuit. Which is denoted by a capital T. So time to complete one circuit, well, we could say it is the distance travelled divided by the velocity. So we might go through 2 pi r, that's the distance for one circuit, and then divide that by the velocity. And then that's giving us a period there. Or we could say that it is the total angle divided by the angular velocity. Right, so this is where we're going to start getting into something interesting, because if we're going to go into the total angle, well, we could say it's 360 degrees divided by the angular velocity if we're working in degrees. Or we could say that this is 2 pi divided by the angular velocity if we're working in radians. So that is in degrees and that is in radians. So why have we picked this 2 pi to be this radians unit of measuring angle? What's so special about this 2 pi rather than this 360 for degrees? Well, let's compare. So if I rearrange the period formula, we're going to see that the V is 2 pi r over t. If I rearrange the period formula for omega using, well, radians, or well, either of them, we can say that omega, the angular velocity, we can say is 2 pi over t, or we can say it's 360 degrees over t. Right, now one of these is particularly useful because if we stick in, so this one depends on radians, this one depends on degrees, this one for velocity doesn't matter which angle we're using because we've got distance over time. But if we've chosen radians rather than degrees, we can now take that and say that velocity is equal to omega r. Now we can't say that if we're using degrees, because here we'd now have to say that velocity is going to be equal to pi over 180 times omega r, and that is a mess. So any time that you do any of this sort of analysis, whether it's in circular motion, when you're doing trig in calculus and things like that, this is why we have to change to radians all the time. If you try and do trig calculus using degrees, then you have to have this factor of pi divided by 180 just cropping up everywhere. It makes everything a complete mess. So why don't we just stick in radians, and then we've got this lovely relationship here that the V is equal to omega r. Right, oh yes, one other bit of terminology that is going to be useful is, so we've said the period, capital T here, which is how long it takes to complete one circuit. So we're also going to want to have the frequency. So that is the number of circuits that are completed every second. So the frequency F is 1 over T. So they're the things that we've got set out here, all in all. We've got these relationships here. We've got this expression for V. We've got this expression for omega. We've got the relationship between the two of them, and then we've got the relationship between frequency and period. So that's all of the terminology put in place that we're going to want to be using here, at least to begin with. We are going to develop 2 more really important bits of terminology. Right, the final pieces of the jigsaw here are when we start looking at forces. So I've put centripetal force up here. You've probably heard of centripetal force and centrifugal force, and these lie at the heart of our analysis of circular motion. So we want to do a more detailed analysis of things moving in circles to see where forces kick in. Now we have to have forces because if something's moving in a circle, its velocity is changing. And we know its velocity is changing because its direction of motion is changing. So if you've got a change in direction of motion, you've got a change in velocity. If you've got a change in velocity, you've got an acceleration. And if you've got an acceleration, as Newton's laws tell us, then you must have a resultant force acting on the object. So we want to analyze motion in a circle and pull out what we can about these forces. Now you can do this analysis in different ways. In some ways it is nice to analyze it using polar coordinates, but we haven't used polar coordinates. So this is where you're using a distance and an angle. So you fix an axis, you've got an origin, you set some kind of direction, which is your 0 angle. And if you want to say where something is, say some point up here, then you say, well, what angle do I need to move through? And then how far do I need to move along that line? You've got an r and a theta. But we're not used to doing that. So I'm going to stick with Cartesian approach at the moment. So our I and our J, because we're only in 2 dimensions. It isn't going to be that difficult to do that. But this is just to make a note that you can take either approach. Right, so let's get into it then. We've got our circle. There's the center of the circle. there's the path that we're moving on. We've got our I and we've got our J. Say the object starts off here at some point, so that's t equals 0, and we're already at some angle of theta 0. That's our starting point. Say by the time we've got round to here, we've moved up to some angle theta, and we're going anti-clockwise at a constant angular velocity. So that's our setup. Oh, and the radius is r. So the radius of the circle is r. We're staying at that constant radius. Right, so from a Cartesian approach, we want to say, well, what is position as a function of time? What's our velocity as a function of time? And what's our acceleration as a function of time? Okay, let's put all those out. I'm going to do this as an ij, but I'm going to put them in little column vectors just because I haven't got much width here on the screen. So what is the I component of our position at time t when we're up here? Well, it's going to be r cos theta. Right, so we've got r cos theta, but rather than just putting theta in, I'm going to take a little bit of an extra step, because theta is going to be our initial angle, theta 0, plus omega t, our angular velocity, so that's angle per unit time multiplied by time. So, or in the language that we've used in kinematics, the accumulation of angular velocity is the change in the angle. So the change in the angle, angular velocity times time, that's the accumulation. We can then say, well, what is the j component? Well, it's the sine of that angle, r sine theta 0 plus omega t. So that's pretty easy to write out what our position vector is. Now we just got to differentiate that twice, and we've got our velocity and our acceleration. We're differentiating with respect to time, so we have to remember when we differentiate our trig functions, we have to differentiate the content of the bracket, as in the angle, and pull that outside as well. So these omegas are going to keep popping out, because theta 0 is a constant, so that just disappears. And then we're going to differentiate omega t to get an omega that's going to jump out the front. So differentiating the I component, minus r omega sine theta 0 plus omega t, and then we've got r omega cos theta 0 plus omega t. Differentiate it again, minus r omega squared cos theta 0 plus omega t, and then minus r omega squared sine theta 0 plus omega t. Right, there's two things that we want to pull out all of this. We want to look at magnitudes and we want to look at directions, because of course forces, well, all of these things are vectors, but we want to get down to the forces. So we want to say things about magnitude and direction. Right, let's start with the magnitudes. So let's do a sanity check for the magnitude of our position vector. Now, obviously, we want this to turn out to be r, because it's staying at a radius r from the center all the time. So the magnitude of our position vector here should be r. So if we were going to get the magnitude of this, you're going to square each component, add them, and then square root. So we're going to have r squared cos squared, all of that, and r squared sine squared, all of that. Well, cos squared plus sine squared is 1. So we're just getting r squared, which we square root to get r. So that looks great. It also gives us the path to getting the magnitude of the others. So the magnitude of v is just going to be r omega. Well, I'm going to write it as omega r because that's how we wrote it on the previous sheet. That was the finding that we had, wasn't it? That was the finding we had, was that the velocity, or the speed around the outside, is the angular velocity times the radius. Now, we've only got that finding. You'll notice there that finding has come out by doing trig calculus. And the only reason the trig calculus works is because we were using radians, which is why we've got the answer for radians here as the relationship between the speed and the angular velocity. We'll then do it again. We've got the magnitude of the acceleration is equal to omega squared r. So we've now got, and this is something that we're going to use loads, acceleration is equal to omega squared r. We also know that v is omega r, So that is v squared over r if we just replace omega. This gets used all the time in circular motion problems. So this is a reusable result that's very easily derived, as we've shown here, and is epically useful. The only thing we're missing is the directions. We've got the magnitudes here, but we don't have the directions. Well, the easiest one to see is for the acceleration. So we know that we're measuring here, this position, we're measuring outwards from the origin. That's what we've done with both of these things. When we were setting this up initially, okay, what's our I component? Well, yeah, we're measuring this outwards from the center. That's how we're doing it. Well, you look here at the acceleration. Okay, we've multiplied both of the components by this omega squared, but otherwise we've just got these minus signs thrown here. It's flipped the direction. So it's changed the direction. If we're measuring position outwards, we're measuring acceleration towards the center of the circle. So this is saying this is towards the center. And that is why I've put centripetal force as the title of the slide, because centripetal force acts towards the center of the circle. Centrifugal force is a force that would act outwards. Now, I'm not going to get into the details of centrifugal force in this video because it will go on far too long. But I have a separate video looking at fictitious forces in general, because that is what centrifugal force actually is. It's an illusion. It's a force that you think exists if you're the thing that's moving in a circle. But if you want to know more about that, go off to the separate video. All we're concerned about here is we've shown that the acceleration is acting towards the center of the circle. So what can we say about the direction here of the velocity? Well, another way of looking at the direction of the position is, let's think of it as a gradient of a line. So the gradient, we're taking the j component and we're dividing it by the I component. So if we do that for position, we've got r sine of the angle divided by r cos of the angle. So we're getting tan of all of that angle. If we do this, so that was for S. If we do this for V and we do the same thing, then we've got cos divided by minus sine. So we're getting minus cot of the angle. That is what our gradient is there for the velocity. Now, you think of how this compares to how do we know if two lines are perpendicular to each other? Well, they have to have that relationship. If one of them has got a gradient of m and the other one has got minus 1 over m, then they're perpendicular. And what is minus cot is minus 1 over tan. So we've got that exact relationship between the position, the direction of the position vector, and the direction of the velocity vector. So if the position is being measured outwards, the velocity is perpendicular to it. So we've said now everything about position. We've got the position, direction, I should say. The position vector is measured outwards from the center. The velocity is radial, is tangential, sorry. So position vector is radial outwards. Velocity is tangential, and acceleration is radial inwards. And we've also got the relationships in magnitude. The velocity is omega r, acceleration is omega squared r, which is also v squared over r. So we've got all of those findings have dropped out, and that is our complete set then of information that we're going to use for analysing circular motion. And we will use this alongside Newton's second law, because we're still doing F equals ma on problems. If something's moving in a circle, we're still using Newton's second law. You know, that applies to all of the motion that we're looking at. But now we've got something we can use for A. As soon as we know it's moving in a circle, our acceleration must obey these rules. So we've got extra information which is specifically for circular motion. So that's why we're deriving this and looking at this case in particular. The final question that we have then when it comes to looking at circular motion is where are we getting this centripetal force from? Now, centripetal force, it's not a new force. It's not like tension or friction or weight or something like that. It's a category of force where anything could be the centripetal force. So what do I mean by that? Let's think of some specific examples then of things that are moving in circles. So say we've got an object that is hanging on a string and we're spinning it in a circle. So we need a force that is going to be acting towards the center of the circle. So in this case, we've got tension in the string, and the tension will then supply the centripetal force. So this is what I mean by the centripetal force. It's not a new force. It's a category that is fulfilled by a different force. So in this case, the tension is the centripetal force. Right, so let's think of another one, a washing machine. So you've got clothes that are spinning around on the inside of the washing machine. They've got a reaction force from the outside of from the drum of the washing machine, which is pushing it in towards the center of the circle. So it's the reaction force from the drum on the clothes that's providing the centripetal force. So this is a completely different thing now. It's now the reaction force that's the centripetal force. If you're on the London Eye, so you're standing there in a compartment on the London Eye. So what is it as the compartment is moving around? Now the compartment is on a big pole that's attaching it. So again, you've got the tension in the pole that's pulling the compartment towards the center of the circle. So that's one centripetal force from the point of view of the compartment, but you're not attached to the pole. You're just standing on the floor of the compartment. All you know about is your feet are touching the floor. So what's the only force you've got kicking around? You've got friction. If there was no friction, as the compartment moved around, you'd just slide off and then smack into the outside wall, in which case you'd then have the reaction force of being smushed against the outside that would then make you move in a circle. But if you're not just sliding off, you've got friction acting here, and that friction is holding you in place and providing the force that acts towards the center of the circle. Of course, I mean, if you're at the top, very top of the London Eye, well, you've got weight acting down as well. So you can have a combination of these things. You're at some angle over here where you've got weight acting down, you've got a component of that weight acting towards the center of the circle, and then you've got friction, which is acting that way, and you've got a component of the friction, which is acting towards the center of the circle. So centripetal force can be built up through multiple forces. The key thing is we need to have a resultant centripetal force acting towards the center of the circle, which is equal to mr omega squared, or mv squared over r. And of course, the v and the r and the omega, these are all properties. The r is the property of the circle, and the omega, or the v, is the property of how quickly we're moving around it. So this is what we're building up when we're doing our problem solving in this. So I'll have more of this when I get onto the questions, and that's probably a good place to move to now. Start looking at some example questions, and you'll see how we're putting all of this analysis together. But this is just an extension of dynamics questions that we've already done.